Hello everyone again. This is lecture 2 of work, energy, and power. In the previous discussion, we just started with the introduction in which we understood about scalar product. Let's move forward with that concept discussion only, and then we can understand the work energy theory. So, this is lecture number 2. I'm Samir Lawankar. This is chapter work, energy, and power. Let's start our discussion. Okay, so currently we are on the first topic only, that is understanding of scalar introduction, which is understanding of scalar product. So we are just understanding the scalar product only. So in scalar product of two vectors, we got to understand the mathematical formulation which says that A dot B is nothing but equal to magnitude of A into magnitude of B into cos of theta. Okay, so that was a simple explanation. So let's move forward with this discussion. Okay, so we understood that these have properties such as A dot B is equal to B dot A, and also has a property distributive law which says that A dot B plus C is nothing but equal to A dot B plus B dot C. We also understood the same concept, that is scalar product concept for unit vectors, and finally completed our discussion for the first lecture. Okay, so let's begin our discussion from directly there, and then let's move forward. Okay, so first of all, we understood the basic meaning of everyday language words of work, energy, and power, and we went on to understand the scalar product of two vectors. And now let us begin our discussion from this concept. Okay, so in the last, at the very last, I explained you the concept of resolution of vectors basically. So in resolution of vectors for 2D space, vector A is nothing but equal to the summation of two different vectors which are in, let us suppose, I and j cap space, or I cap and j cap. So the magnitudes will be represented as ax and ay, right? If we increase it to 3 dimensions, what we can say, it is for 3D space, the vectors can be written as vector A is nothing but equal to summation of 3 different vectors, that is I cap, j cap, and k cap, which is equal to ax, ay, and az. Okay, so I hope it is clear that this is the complete concept of resolution of vectors which we understood in the chapter motion in the plane. Okay, so now let us suppose, let us understand this concept only here. So ignore this for now. Okay, so let us say that we have some vector A which is nothing but equal to ax I cap plus ay j cap plus az k cap. Okay, and let us say we have some another vector B which is nothing but equal to bx I cap plus by j cap plus bz k cap. Okay, so that thing being said, it was given that we have, let us say we have these two vectors. Now let us try to find out the scalar product of these two different vectors, these two vectors. Okay, so let me do the complete calculation here so that you can understand bit by bit what is happening. So A dot B, correct, which is equal to A dot B is equal to ax I cap plus ay j cap plus az k cap dot product with bx I cap plus by j cap plus bz k cap. Correct? Now, from the previous discussion, we know, what do we know? First of all, we know that A dot B plus C is nothing but equal to A dot B plus A dot C. And we know that I cap dot I cap is equal to J cap dot J cap is equal to K cap dot K cap equal to 1. Also, I cap dot J cap is equal to J cap dot K cap is equal to K cap dot I cap is equal to 0. Okay, so I think we have clearly understood how these things are derived, and we know these complete formulations. We know the distributive law also, so this is nothing but your distributive law. This is nothing but your distributive law, and this is nothing but the properties being explained. That is, I cap dot I cap is equal to j cap dot j cap is equal to k cap dot k cap, which is equal to 1. And similarly, I cap dot j cap is equal to j cap dot I cap, k cap is equal to k cap dot I cap, which is equal to 0. Okay. Now let us try to use this in this form. Okay. If you see clearly, let us suppose this to be your A for now, and this to be your addition of something which is B plus C plus, let's say, D. Okay, so how can we write this? We can write this as nothing but A dot B plus A dot C plus A dot D. After writing this, again what we can say, let us say we take this as A now, and again this as B, C, D. So we can write plus this multiplied by this plus this multiplied by this plus this multiplied by this, because it follows distributive law. And again we can just multiply this with all these three terms again. Correct? So that is only we are going to do here, and then we can analyze further situation afterwards. Okay, so let me do it. So it is nothing but AX BX I cap dot I cap. So magnitudes will be multiplied with magnitudes, vectors will be multiplied with vectors. So because it is dot, we will add a dot here. Okay, so you can see clearly dot is being added, which is equal to not like this, let me go in steps only, plus AX BY I cap dot J cap plus AX BZ I cap dot K cap. So first line is done, plus AY BX J cap dot I cap plus AY BY J cap dot J cap plus AYBZ J cap dot K cap. So I think you can understand directly. So first it was I to I, then I to J, then I to K. On this time it's J to I, then J to J, and then J to K. Right? So I'm just doing some procedure-wise multiplication, just using this distributive law. Okay, nothing else is being worked upon. Okay. Again plus, so this time it will be AZ multiplied with first it's BX, so it's K cap dot I cap plus AZ into BY, that is K cap dot J cap plus AZ into BZ K cap dot K cap. Okay, so this is the final formula which we got. Now let us try to use these properties here. Okay, so if you look at this clearly, whatever things will be 0 here, anything which has a property of I dot J, or anything which is a vector, it is I dot J, J dot K, or K dot. Okay, so if you see clearly, this will be 0, this will be 0, this will be 0. I also proved to you that I dot J is also equal to J dot I because of commutative law. Similarly, J dot K is equal to K dot J to commutative law, and similarly K dot I is equal to I dot K for commutative law. This also I proved in the last class only. Okay, so therefore as it is J dot I, this can be also said as equal to I dot J, and hence this will also be 0. Okay, fine. So then this is again 0, then this is 0, and this is 0. Okay, so that leaves us with AX BX I cap dot I cap plus AY BY J cap dot J cap plus AZ BZ K cap dot K cap. Right? Now if you see again the properties here, you can see that this is nothing but equal to 1, this is nothing but equal to 1, and this is nothing but equal to 1. Okay, so what is the final result which we get? The final result which we get is nothing but equal to AX BX plus AY BY plus AZ BZ. Okay, so that is the final formulation which we got for this. Okay. Okay, so now let us look at this very, very carefully. If you look at this very, very carefully, what you will see? What is the product multiplication being done here? A product multiplication which is only and only visible here are the properties or the components which are in the same direction. So here X is multiplied with the vector component of B in the same direction. Similarly, here Y is being multiplied with the vector component of B which is in the Y direction only. And here also the Z component of vector A is multiplied with Z component of vector B. And so that is how the scalar product of two vectors can be multiplied if we know the component vectors of both of them. Okay, so just erasing everything and writing the only formulation which is required here. So if vector A is equal to ax I cap plus ay j cap plus az k cap, and B is equal to bx I cap plus by j cap plus bz k cap, then A dot B is nothing but equal to ax bx plus ay by plus az bz. Okay, so to get these equations, the thing which was required was, first of all, we should know that commutative law is being followed, so that we can convert I dot j, j dot into j dot I, j dot k into k dot j, and k dot I into I dot k. Then next was distributive law which was being used, so as to do the multiplication very carefully. And second thing, the third thing was using the usage of these properties was being involved. Okay. Fine. So we have understood this complete concept. Now let us move forward. So given two vectors, let us say the A and B are given. Let us suppose this was vector B written here. Okay, sorry for the mistake. So their scalar product is nothing but A dot B, which is nothing but equal to ax bx plus ay by plus az bz. Okay. Now moving forward, what we can say from the definition of scalar product and above equation, what we have. So now let us do one more thing. Let us do A dot A. If we do A dot A, this will be nothing but the component of AX multiplied by AX only, component of AY multiplied by AY only, and component of AZ multiplied by AZ only, which is nothing but equal to AX squared plus AY squared plus AZ squared. Right? That is only written here. That is A dot A is nothing but equal to AX into AX plus AY into AY plus AZ into AZ. So I'm just multiplying the components first in X, then in Y, and then in Z, and then adding all of them. So therefore what we can say? We can say that this A dot A is nothing but equal to square of the magnitude of the vector. Right? We know what is the magnitude of the vector. This is nothing but magnitude. If I square the magnitude, please remember, if I square the magnitude, then this is also equal to ax square plus ay square plus az square. That is only written here. That is the magnitude of the vector is square of the magnitude of the vector is equal to ax square plus ay square plus az square. Clearly? So therefore, what we can say that A dot A is nothing but equal to magnitude of A into magnitude of A into cos of 0 degree, because the angle between them would be same. This is also equal to A square. This is how we denote the square of the magnitude. Okay, fine. Moving on. Now, second property says that, or second explanation discussion says here that A dot B is equal to 0 if A and B are perpendicular. Quite clear. Let us understand this line again here. So let us suppose this is your vector A. Let us suppose this is your vector B. Okay. Let us say this is perpendicular to each other. What is the meaning of perpendicular here? Perpendicular simply means that the angle between them is 90 degrees. So the angle between them is 90 degrees. Then A dot B is nothing but equal to magnitude of A into magnitude of B into cos of angle between them, which is 90 degrees. So let there be any number which is denoting the magnitude of A and B, but as the angle cos theta is 0 here, therefore the complete value will be 0. Okay, so therefore A dot B is 0 if A and B are perpendicular to each other. Fine. So we have understood this complete concept also, that A dot B is nothing but ax bx plus ay by plus az bz. Using this property, we understood that the A dot A is nothing but equal to square of the magnitude of vector A. And again, next thing which we understood was, if that A and B are perpendicular, then the scalar product of two vectors here is 0. Fine. That thing being said, let us move forward and understand this question here. Okay, so that we are clear with the concepts of your scalar product of two vectors. Okay, fine. So find the angle between the force F and the displacement D. Also find the projection of F on D. Okay, so first of all, we need to find the angle between both of them, and after the angle is being calculated, we just need to find out the projection of F on D. What is the meaning of projection of F on D? It simply means, please understand, because this line is very important to understand, correct? Let us suppose this is your F, and let us suppose this is your D. F on D basically means that you need to find out the value when F is being projected here, projected on D. So what is this value? That value is nothing but calculating F cos theta. Okay, so that is the projection of F on D. Fine. So let us start understanding this question here. So here, first of all, F is given to us as 3i cap plus 4j cap minus 5k cap, and displacement D is nothing but equal to 5i cap plus 4j cap plus 3k cap. Correct? Now, let us calculate scalar product of F into D. So this can be equal directly the multiplication of the respective coordinates or respective resolved vector, resolved components. So for F dot D in X direction, it will be 3 multiplied by 5, plus in the Y direction it will be 4 multiplied by 4, and in the Z direction it will be minus 5 multiplied by 3, which gives you 15 plus 16 minus 15. 15 gets cancelled. So this is nothing but equal to 16 units. Clear? Okay. Now next thing is what we can do. Next thing what we can do is we can find the magnitude of F and we can find the magnitude of D. Okay. So how can we calculate the magnitude of F? We know that F dot F is nothing but the square of the magnitude. Correctly? So this is nothing but square of the magnitude. So what we will do? We have 3i cap plus 4j cap minus 5k cap, dot product with itself. So it's 3i cap plus 4j cap minus 5k cap. So let us calculate. It will be nothing but 3 squared plus 4 squared plus 25. So I mean not 25. Let me not write it directly. Plus minus 5 squared. Okay. So that is equal to nothing but your 25 plus 9. So it is nothing but 9 plus 16 plus 25, which will give you 50. So this is 50 units. Okay. Similarly, we can calculate the value of D dot D. So D dot D will be nothing but again, it's 25 square, 5 square is 25, 4 square is 16, and 3 square is 9. This will be again 50 units. Okay. So I hope it is clear till now. Now we basically know what is F dot D. F dot D is nothing but magnitude of F into magnitude of D into cos theta. Correct? We have calculated the value of F dot D here. We know the square of the magnitude of F. We know the square of the magnitude of D. So how can we calculate cos theta? Cos theta can be directly calculated as 16 upon under root of 50 into under root of 50. So I hope it is clear, because magnitude of F will be nothing but equal to under root of 50 from this, because this is square of this, and similarly the magnitude of D will be nothing but again square. Therefore cos theta will be 16 upon under root 50 into under root of 50. Okay, so that thing is only been explained here. Therefore what we got, that cos theta is nothing but equal to F dot D upon magnitude of F into magnitude of D. We calculated F dot D as nothing but equal to 16 upon what is magnitude of F? It is under root 50. What is magnitude of D? It is under root 50, which is equal to 0.32 when being calculated, and hence we got the value of theta is nothing but equal to cos inverse 0.32. Okay. So what are the basic concepts which were being involved here? The first basic concept which was involved here was use of this, and the second concept which was involved here was usage of this thing. Okay, so these were involved in the understanding of this example which we just solved. Okay, fine. So after finding out the angle, the second question is basically you just need to find the projection of F1t. So this projection is nothing but after you understood, calculate the value of theta, what will you basically do? You will just find the value of F cos theta and you can understand the result. So what will be F cos theta basically? It will be under root of 50 into cos theta, which is equal to 0.32, and that is the projection of F on T. That is F cos theta. Okay, so that I think we have understood this. So again, understanding F cos theta. So basically, let us suppose this is your F, this is your D, because we need to find the projection of this on this. Correct. So what you will do, you will just draw a perpendicular, and this will be nothing but your F cos theta. Okay. So I hope it is clear. So that is the end of the scalar product. Everything we have understood till now was being even applied to the one of the example also. We understood different properties of scalar product. We understood different ways in which we can write a scalar product. Different definitions such as projection of A into B and one was B into A, etc. were being explained. So that thing being said, now we know the basics of scalar product. We know the understanding of scalar product, that which is required for understanding work, energy, and power. So let us now start with the concept, the first basic concept of this chapter, which is notions of work and kinetic energy, the work energy theorem. So let us understand the work energy theorem in bit detail. So let's start. Okay. Fine. So first of all, a revision of the motion in a plane. So we understood different kinematic relations. So if you remember correctly, please try to recall this kinematic relation while I explain you here. So first of all, the point to be noted here was kinematic relations are only and only valid in constant acceleration. Okay, so if the acceleration is constant, then only we can write these kinematic relations. Okay. So first of all, the first equation or the first kinematic equation which we got was the final velocity of V. Final velocity is nothing but equal to initial velocity plus acceleration into time. The second kinematics equation which we got was that the displacement S is nothing but equal to the initial velocity. Displacement S is nothing but equal to initial displacement, but initial velocity into time plus half a t squared. Correct? If I write it in more general form, let us say I say this as nothing but your vector r, that is position vector r, so it is nothing but r is equal to r naught. Okay? And the third was basically that the square of the final value is equal to the initial value, that is v naught square, plus 2 into a into, let's say, r minus r. Okay? Right. So these are the kinematic relations. Now let us start understanding whatever is written. Okay. So the following relation for rectilinear motion. What is the meaning of rectilinear motion? Rectilinear motion is a motion in a straight line under constant acceleration. So I just explained that these kinematics equation was valid when acceleration is constant. Okay. So the following relation for rectilinear motion under constant acceleration A has been encountered in the previous chapter. Okay. So what is that relation? It is nothing but V square is equal to U square plus 2AS. So I can also write this as equal to V square minus U square is equal to 2AS. Okay, what is S here? S is the displacement. What is V small v? Final velocity. What is small u? Initial velocity. It is also written here where small u and small v are the initial and the final speeds, and S is the distance traversed. Fine. Now multiply both sides by m by 2. Okay, so let me multiply this side also by m by 2 and this side also by m by 2. Okay, so therefore this side will give you half m v square minus half m u square, which is nothing but equal to this 2 and 2 will get cancelled. This will be equal to mass into acceleration into displacement. So now in the chapter of laws of motion, we have understood clearly what is mass into acceleration. This is nothing but called as force. Okay. So therefore what we can write? We can write half mv square minus half mu square is equal to force into displacement. Okay. where the last step is from follow second Newton's second law. So we understood that MAS is also mass into acceleration is also your force into displacement. That thing being said, now we can generalize above equation to three dimensions by employing vectors. So now let us employ vectors here. Okay, so if we employ the vector, that this relation can be written as v square minus u square is equal to 2 into a dot d, or a dot. So d is the displacement here. Fine. Let us multiply again with m by 2 on both sides. So that is nothing but equal to nothing but half m b square minus half m u square is equal to, this 2 and 2 will get cancelled. It is nothing but m into a dot d. M into a will give you f dot d. Okay, so only a dot d is a vector here. Therefore, we got that f dot d is the vector representation being explained here. M is a scalar, correct? M is a scalar. So it is nothing but your m dot f dot d, that is equal to half mv square minus half m. Okay, so this is something. So this is nothing but till now we have just did some mathematical calculations from so that from this equation we can finally get up to this equation. Okay, let us understand why we did all these things. Okay, so what was the basic reason of doing all these things? So the above equation provides a motivation for the definitions of work and kinetic energy. So let us understand first of all what is this kinetic energy word again and again we are using. Okay, the left side of the equation. So let me write the equation here again in the vector form. So it is half mv square minus half mu square is equal to f dot d. Okay, so what is the meaning here? So what is the meaning here? Basically, the left side of the equation is the difference. As you can see, it's a difference in the quantity. What is the quantity? It's half the mass times, as you can see, it's m by 2, that is half the mass, times the square of the speed. So it's square of the speed also and half the mass also. Correct? So half mv square. Okay. So the left side of the equation is the difference in the quantity, half the mass times square of the speed, from its initial value to its final value. Okay, so this is your final value and this is the initial value. We just did the difference of both of them. We call each of these quantities as the kinetic energy. Okay, so basically kinetic energy can be written as nothing but half m v square. V is the velocity here, so basically we can write as u also. Okay. So therefore, we call each of these quantities as the kinetic energy, which is denoted by K. So that is how we denote it. So it is also referred to as work K. What is the right side? The right side is the product of displacement and the component of force along the displacement. Very important line. It is not just the product of displacement and force. It is a product of displacement and the component of force along the displacement. Okay, let us understand this line first of all and then we can move forward. Let us suppose this is one of the planes. Let me make it much more straighter. Let us say this is one of the plane, okay, on which an object is being kept. Let us say this is the object is being kept, correct? It has some mass. Let's denote that mass by m. Okay, and now this was the original position, correct? Let's say if I using a hand, I was pulling it in this direction. Okay. Let us suppose the mass was this much that it cannot leave the contact of the plane, and it is moving in this direction. So this is the direction of its moving. Okay, so this is the direction of its moving. It moved from this position to, let's say, this position. Okay, so what is the work done here? The work done will be nothing but equal to this value of displacement multiplied by the component of force which is in this direction. So what is the component of force in this direction? It is nothing but F cos theta. Correct? Therefore, it is also equal to f cos theta multiplied by d, which is nothing but the concept or the word work is used in physics. So basically, what is work done? Work done nothing but f cos theta multiplied by d or f dot d. So it can also be written as f into d into cos theta, or f cos theta into d, or f into d cos theta. And wherever, however you require, you can use them. The answer would be same. Okay. Now let us complete this discussion here. So this quantity is called as work. So this is nothing but your work. Okay, and is denoted by capital W. Therefore, what we got that the difference in the final and the initial energy is the total work done. Okay, therefore Kf, that is the final kinetic energy, minus the initial kinetic energy is nothing but equal to the total work done. Okay, so this is the formulation which we got, that the difference in the kinetic energies is nothing but equal to the work done. Okay, where Ki and Kf are respectively the initial and the final kinetic energies of the objects. Right? So that thing being said, we have just derived a new formula. Let us suppose the derived new formula says that the difference in the kinetic energies, that is half mv square minus half mu square, is nothing but equal to, we can write it as also equal to delta Ke. Correct? We understood the concept of delta in the initial chapters, that is final minus initial of Ke. Ke is nothing but your kinetic energy here. So here it is written as delta K only. So let me write it as also delta K only, which is nothing but equal to F dot D. Okay. So it can be written as also equal to magnitude of F into magnitude of D into cos theta. Right? So that is the complete formulation which we understood in the previous. Okay. Achha, we understood one more thing. We understood that what is work? Work is nothing but equal to F cos theta into D, or F D cos theta, or F into T cos theta. Okay. The work refers to the force and the displacement over which it acts. Okay. So what does work refers to? It refers to the force. It refers to the force and the displacement over which it acts. Okay, so it has its work depends upon the force and the displacement. Okay, now work is done. Work is done. Please remember, now we are talking in physics terms. Okay, so work is done by whom? It is done by the force on what? On a body over a certain displacement. Okay, so in physics, work is done by what? It is done by a force on the body. It is done on the body over a certain displacement. So what are the factors required here? The factors required here are force and displacement. Okay, fine. So if that thing is being said, let us now understand the work energy theorem. So what is the work energy theorem? The work energy theorem simply states that the change in the kinetic energy, so this is the change in the kinetic energy of a particle, is equal to what? It is equal to the work done by it on it by the net force. The work done on it. So this is the work done basically, or this is the work done basically. The work done on it by the net force. So what is it using the last word? Net force. So net force basically means, let us suppose this is an object. This is one force acting on it. 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 Okay. Let us suppose by some way or the another, we analyze that all the summation of these forces is nothing but equal to some force which is F net. Okay. This F net leads to this displacement S. Okay. So if we can find this F net, we can find this S, and this change in kinetic energy which would have happened is nothing but equal to this F net dot S. So that thing is only been explained by the concept of net force. Okay. So iterating the work energy theorem again. So the work energy theorem simply states that the change in kinetic energy of a particle is equal to the work done on it by the net force. So mathematically, it is nothing but that half mv square minus half mv square minus half mu square is nothing but equal to m into a dot t, or more generally f dot t. Okay, so in left side is basically kinetic energy difference and right side is basically the work. Okay. So we shall generalize the above derivation to a varying force in a later section. Okay, so here the force was considered to be constant throughout the time. Let us understand in the later sections what will happen when the force is varying. Okay, so basically when the force is varying, we'll distribute it into very small time intervals and understand that what is happening. Okay, so only differential calculus would be used, nothing very typical or complex would be used. A simple use of differential calculus will make us understand this varying force concept also. Okay, so we'll understand that in the later part. But till now, we have understood the scalar product of the two vectors. Then we understood the basic definition of physics meaning of work. We understood the concept or the meaning of the word kinetic energy, and we understood the work energy. Okay, so that thing being said, now let us move forward and understand this example regarding these all concepts. Okay, moreover about the kinetic energy and work energy theorem. Okay, so let us understand. So it is well known that a raindrop falls under the influence of the downward gravitational force. Correct. So this follows or it goes downwards due to the gravitational force acting. Correct. What is the gravitational force? Gravitational force is nothing but m into g. Correct. And the opposing resistive force. There is a resisting force in this direction. Okay. The latter is known to be proportional to the speed of the drop, but is otherwise undetermined. Okay, so this is said to be proportional to the speed of the drop. So it depends upon the speed in which it is going downwards. Okay, so it depends upon the speed of the drop, but is otherwise undetermined. Otherwise, we cannot find the value. Okay. Let us consider the drop of mass 1 gram. So the mass of drop is given as 1 grams to you, or we can write as 10 to the power minus 3 kgs. Okay, and the height is given as, so h is given to you as 1 kilometers. You can also write 1 kilometer as 1000 meters. It hits the ground with a speed of 50 meter per second. So v final is given to you as 50 meter per second. As nothing is given about initial velocity, we can assume the initial velocity to be equal to 0. So initial velocity is 0 meter per second. Okay, so mass is given to you. Then next thing is height is given to you, and the next thing is the speed with which it hits the ground is given to you. Okay. The first question asked is, what is the work done by the gravitational force? Okay. So work done by gravitational force can be calculated how? It can be calculated. So the total work done, as nothing is given even about the resistive force, we can assume this to also be equal to 0. Okay. So first of all, let us calculate the work done. So work done will be nothing but equal to what is the force, and as you can see that the work done by the gravitational force will be in the downward direction. So the displacement is also in downward direction. So the amount of angle here will be equal to 0 degrees. Okay. So what is the force here? Force is nothing but equal to m into g, and what is the displacement? That is nothing but h. Okay. So therefore, what is mass? It is nothing but 10 to the power minus 3. The value of g is unknown, or we can take it as here 9.81, and height is nothing but 1000. Okay, so this is one of the way in which we can solve this problem. Another way in which we can solve this problem is using your concept of kinetic energy change. Okay, so what is the change in kinetic energy here? You can see clearly. That change in kinetic energy is nothing but equal to the final value, that is half mv square, minus initial value, that is half mu square. Correct? So this is nothing but equal to, as we know that the initial velocity is 0 and the final velocity is nothing but 50 in square. Correct? So if you just solve this, you will get the answer as equal to 1.25 joules. Okay, so we have assumed, so it is written here also, where we have assumed that the drop is initially at rest. Okay, so the change in kinetic energy of the drop is this much. Fine. So assuming that g is constant with a value of 10, the work done by the gravitational force, in the starting only we have understood this, that the work done by the gravitational force will be nothing but equal to force into displacement into cos of 0 degrees, which is nothing but equal to m multiplied by g multiplied by 1, into height multiplied by 1. So mass is given to you as 10 to the power 3. They have assumed G as 10 and assumed the value of height as 1000. So therefore, this and this getting cancelled. This will be 10 joules. Okay. So the first thing we asked was what is the work done by the gravitational force? Therefore, the work done by the gravitational force is nothing but equal to your 10 joules. Okay. Now let us look at the second question. The second question says is what is the work done by the unknown resistive force? Okay. Now using the work energy theorem simply, we know that kinetic energy is nothing but equal to total work done. Correct? What is the change in kinetic energy? Change in kinetic energy is nothing but equal to 1.25. Correct? That is nothing but equal to the work done due to gravitational force and work done due to your resistive force. Okay. So what is work done due to resistive force? This work done due to resistive force will be nothing but equal to 1.25 minus 1.25 minus your 10, which is nothing but equal to minus 8.75 joules. So you can see clearly that this resistive force work is being done in the negative direction. Okay. Fine. So that is how we can understand this concept also. That is the work done. So basically, WR is the work done on the resistive force, and thus this work done is nothing but equal to minus 8.75 joules, which is negative. Okay. So work done, total work done came out to be positive. The total work done due to gravitational force was nothing but M multiplied by G multiplied by H. And because we cannot determine the proportionality sign of, or basically the concept of how this resistive force is being acted upon, therefore we found it out using the work energy theorem. Okay, so the basic energy usage of work energy theorem is nothing but the total kinetic energy is nothing but equal to Wg plus Wr. Okay, fine. That thing being said, that is the end of the discussion regarding the scalar product and the work energy theorem. Now let us start the new discussion regarding the concept of work. Okay, clear. So let us now start with the basic introduction about force, displacement, and its scalar product vector here. Okay, let's start. So as seen earlier, work is related to force and the displacement over which it acts. So just now in the previous discussion only we have understood this line that work is nothing but related to force also and displacement also over which it acts. Consider a constant force. Please remember we are only working with constant force for now. In the next subsequent slides we will understand variable force also. So variable force basically means that with change in time there will be change in the value of F. Okay. Constant force here basically means that with the change in time the value of F is constant. Okay. Fine. So let us start understanding this concept here. So the object undergoes a displacement d in the positive x direction as shown in the figure. So you can see that there was an object kept here. It has moved to this location. And because it has moved to this location in this right hand side direction, generally our sign convention says that when we are moving towards right, we consider the displacement to be positive. Okay. So the object undergoes a displacement d in the positive x direction as shown in the figure. Okay. Now, the work done by the force is defined as what? It is defined to be the product of the component of the force in the direction of the displacement. Okay. So the component of the force which is in the direction of displacement. So what is that? It is nothing but F cos theta, right? And the magnitude of displacement. So that is nothing but how a work is being defined. Okay. In mathematical form, what we can write? We can write that this is nothing but equal to W, which is equal to F cos theta into D. Also, it can be written as nothing but scalar product of F and D. Okay, that's nothing but scalar product of F and D. Right. Moving on. So we see that if there is no displacement, there is no work done even if the force is large. Okay, so this basically means, let us take for one thing for an example. Let us take this as an object A. It has a mass M and let us suppose we are applying some force, let's say 100 or 1000 kilonewtons. Okay. This force has such a huge mass or is such impacted upon the ground that it cannot be displaced from its location. So let us say that if the displacement is zero, then what is the work done? The work done, or let's say I don't know it by F, I denote it by D only. Then work done will be nothing but equal to F cos theta into 0, and this will be equal to 0. So work done will be 0. Okay, 0 units. So we see that if there is no displacement, then there is no work done even if the force is large. Okay, so one of the example, thus when you push hard against a rigid brick wall. So let us say this is the brick wall and you're trying to push hard. So let's say your hands are being impacted upon like this at these locations. Okay, and you are trying to push it. So basically pushing means you are trying to apply a force in this direction. Okay, so even if you try to push hard against this rigid brick wall, the force you exert on the wall does no work. So why is no work is being assumed here? Because the displacement d of this wall is 0. Okay, so the displacement d is 0. That means the work done will be nothing but equal to this F into 0. Let us suppose this F and d are in the same direction. Then we can say that the work done is okay. So thus, when you push hard against a rigid brick wall, the force you exert on the wall does the work. Yet your muscles are alternatively contracting and relaxing, and internal energy is being used up, and you do get tired. Okay, so this is how we understand this in the everyday language sense. That is, we say that okay, some amount of work is done because our heads are paining, our legs are paining. So that is the work done, which is generalized in everyday language sense. But in physics terms, you have done actually more. Okay, so yet your muscles are alternatively contracting and relaxing, and internal energy is being used up, and you do get tired. Thus, the meaning of work in physics is different from its everyday usage. Okay, so I think you may have already understood this line. That is that the meaning of work in physics is different from its uses in everyday life. Okay, fine. That thing being said, now let us move forward. Okay. So now there are basic instances so as to understand when can we say that no work is being done. Okay. So first of all, in the first sequence, see, so when no work is done is basically meaning that the displacement is 0 as seen in the previous example. In the previous example, that the displacement was 0 as even if you try to push the wall, there is no displacement, and hence we can say that the work done is 0. Okay, so moving from this location, one more example written here. Let us suppose there's a weightlifter, and let us suppose these are your barbells being kept here like this. Okay, now what is the basic general agenda of doing the weightlifting? Using your hands, you keep your hands here, you try to pull this weight towards the upward direction, and after a limited amount of time, you again put it downwards. Correct? So if you directly look at this location of the barbell here or the dumbbells here, you can see that the amount of displacement of this is 0. The displacement is 0 in physics term. What does it mean? That the work done is 0. Correct? That is how you can understand this relation here. The weightlifter holding a 150 kg mass steadily on his shoulder for 30 seconds does no work on the load during this time. Okay, a similar case scenario can be observed in this form also. Let us say again, this person is there, he tries to hold this at this location. So during the time interval from t is equal to 0 to t is equal to 30 seconds, let us assume that it is at this location only. So because there is no displacement of this barbell or this dumbbell during this time interval, what we say that the amount of work done here would be equal to 0. Okay. Fine. So that is the first understanding we observe for when is no work done. Let's move forward. Understand the second example here. So when the force is 0. Okay. So let us say a block is moving on a smooth horizontal table, is not acted upon by horizontal force since there is no friction but may undergo large displacement. Okay. So let us say I'm just giving a pictorial representation of the example here. Let us say this is a table which is frictionless. Okay, so when the frictionless table is being interacted upon, if you leave a box here, there is a general tendency that it may go in some sort of some way or another. But as the force applied, the external force applied on it is 0. The external force applied is 0. So again, what we can say that force is nothing but equal to F cos theta into D. But D may be very, very large. The theta may also have some values, but as the value of F is equal to 0, therefore the work done is equal to 0. Okay, hope it is clear to you. Moving forward. So we understood this, Now let us understand the third point, that let us say that force and displacement are mutually perpendicular. Now this is a very important case to understand, because here force is also having some value, displacement is also having some value, but because only and only because those are in perpendicular to each other, hence the work done in physical terms would be equal to 0. Okay. So let's understand that statement here. So the force and displacement are mutually perpendicular. This is so because theta is nothing but equal to pi by 2 radians, which is equal to 90 degrees. Therefore, cos pi by 2 is 0. So basically what is happening? F dot D is nothing but equal to magnitude of F into magnitude of D into cos of 90. So because cos 90 comes, we know this is equal to 0. Therefore, work done is nothing but equal to 0. Example written here. So for the block moving on a smooth horizontal table, the gravitational force mg does no work as it acts at right angles to the displacement. So basically what is happening, let us suppose this is some object m. Okay, so the gravitational force which is acting on it is mg. Right, let us say this is kept on a table. Correct. So and due to some force F, it is moving in this direction with the displacement s. Okay, so basically because the displacement in this direction is 0, the displacement in this direction is 0, what we can say basically that this force has nothing to do with this force. This mg force has nothing to do with this displacement. So if you try to find out the work done here, this work done will be nothing but equal to mg into the displacement into cos of 90 degrees. Correct, because the displacement is perpendicular to the force, and hence this will be equal to 0. Right. So just the last line for this lecture here. So if we assume that the moon's orbit around the earth is perfectly circular, then the earth's gravitational force does no work. The moon's instantaneous displacement is tangential while the earth's force is radially inward. So basically what does it try to say to you? That let us suppose that this is earth, correct, and there's a moon orbit. So let us suppose the moon is rotating around this. So let us suppose this is the moon. So it is just saying that if we assume that the moon's orbit around the sun is perfectly circular, then the earth's gravitational force does no work. Why it is being said like this? That the moon's instantaneous displacement is tangential. So at that particular instant, the displacement is in this direction, and the earth's force is radially inward. So basically the force is like this. Because force is like this, let us go, this is the center. So as there is a 90-degree angle being made here, therefore work done will be again F into D into cos of 90 degrees, and hence this will be equal to 0. So therefore as theta is pi by 2, so 90 can also be written in pi by 2 radians. As theta is pi by 2 radians, therefore work done is nothing but equal to 0. Okay, fine. So we understood when what are the three examples in which work done can be said to be 0. Right, that thing being said, let me stop the discussion here only. From this point onwards, we will understand in the next lecture. So the course progress for you, we started with the introduction, and right now we have completed the work energy theorem, and we are in the third point, that is work. After this, we will understand more about kinetic energy, then we will understand the work done by the variable force, and then move forward with all the concepts which are being written. Okay, so that thing being said, let me stop this lecture here. So thank you so much.